So good evening, everyone. Happy to see you all. So I'll just start this webinar. So today we were talking about the concept. Today the topic is uh, foundational, math for CFD. Actually, in fact, I'm trying to make this like a series, uh, like part 1, part 2, part 3, like that. Let's see how it goes. Okay. So are my slides visible, Mehul?
Yes, Venkat sir.
Yeah, fine. So, basic math, you can give it different names, of course. So the agenda is, I have put all these topics, but let me see how much I can cover in this short time. So mostly I'll be doing it like 45 minutes to 1 hour. Let's see how we can make it interesting. I'll also try, because math generally is not so easy sometimes, right? Yeah, so this is like the first of the series. It might be a little rusty, but let's see how it goes. So we'll be covering about some basic definitions that come along in computational fluid dynamics, CFD. We'll talk about some of the basic equations that generally again show up, and what are the basic mathematics that is required for us to understand the different solution methodologies to solve these equations, right? So this is so what is CFD, right? CFD is computational fluid dynamics. I think everyone of you know. It is nothing but the analysis of fluid or heat flow, by a computer using numerical methods. That's the you can call the definition here, which I have written. Another way of putting the same thing is CFD is all about solving mathematical equations that describe the flow physics in space and time for meeting certain goals, right? Or for meeting certain targets. We don't just do a simulation, right? There is some target or a goal that we are actually aiming for. So that is the definition of CFD. And here, so here if I look at the mathematical equations, right, and the flow physics, so all of you are aware, right? If you take the Newton's first law, F is equal to ma, you know, that's a general physics-based concept, but very nicely put in mathematics, right? So most of the physics, ultimately, even though we theorize and we do a lot of quality stuff there, qualitatively we try to explain. Ultimately, mathematics has to come to rescue for giving some quantitative aspect for our assumptions, theorems, and assumptions to validate our assumptions also. So physics and mathematics go hand in hand. And here we are doing fluid mechanics. So when you say fluid flow, it also, when you say the physics, right? So what are the different fluid flow physics that are generally modeled in using CFD? So one is fluid dynamics, then heat transfer, thermal analysis, then thermodynamics, chemical reactions. Then we have multi-phase flows, right? So there are so many different wonderful physics that are actually being captured by different models. And these models are all mathematical models that are trying to capture the physics, right? So there are a lot of mathematical equations and models to uh, give a form to the physical laws, right? And so we are solving the governing equation. These mathematical equations are the governing equations, which are generally the Navier-Stokes equation that we use in CFD extensively. So these are nothing but conservation equations. Can anyone tell me like what are the different conservation equations here? Just put in the chat box. Navier-Stokes equations. Yeah, continuity equation is for which parameter? Conservation of mass and energy. Very good. Mass, and there is one more parameter, right? Not Bernoulli. Bernoulli is a derivation of Navier-Stokes. So conservation of mass, energy, and then one more is there. Yes, momentum. Great. So momentum equation. Actually, the Navier-Stokes equations are based on the momentum equation alone. The continuity and energy are added to it, and then the whole set is called as Navier-Stokes. Actually, Navier and Stokes worked on the momentum equations first. Okay, great. Very happy. Thanks for participating. So, how are we solving? Using computers, right? In the olden days, we didn't have a lot. These methods were there. The mathematics were there. The physics were there. The numerical methods were there. But we didn't have very fast computers. The fast computers have just showed up like last 20, 30 years. And that's why this subject and other simulation areas also like CAE, it can be electronics, it can be computer science. All these have boomed because of very high computational power that we have at our disposal, right? So we are using computers to solve these equations. And where are we solving these equations? In space and time, obviously, right? It can be a turbine, it can be a compressor, it can be a flow past a car. There are so many situations that we are using CFD, right? Nowadays, even for sports also. So everything, all these components or parts are in bounded in space. So this is the domain, the geometry, because the set of Navier-Stokes equations are the same, but how are they producing different solutions? Can anyone tell me? The Navier-Stokes equations are the same, right? Whether you're solving a aeroplane problem, whether you're solving a ship problem, or a turbine, or a compressor, or a pump, you are using the same set of equations. But how did the solutions change? That is the beauty of it. Can anyone tell me here? Why does the solution of the same set of equations change for different applications? Density. Density is a property of fluid. So, okay, you're saying fluid is changing. That is one thing. Very good. Boundary conditions. Right? Boundary conditions are different for different problems. And also the fluid, as you told. Okay. Boundary conditions is very important. The domain also, right? The geometry. The geometry of airfoil, or an aeroplane, of an automobile, of a pump, they're also different. Of a valve. So the geometry is different. The boundary conditions are different. And as some of you have told, the fluid itself might be different. So if you're flowing air, whether you're flowing water, whether you're flowing honey, so the fluid also will change. So all this creates so much complexity that these Navier-Stokes equations are the hardest to solve, and there is actually a $1 million. It's one of the $1 million challenges. So if anyone of you solve this, it's an open challenge. They will give you $1 million. Okay. Now, why are we doing all this? To meet certain goals. What are the goals? So if you're dealing with some pump or a turbine or a fan, we are trying to optimize the flow rate. We are trying to optimize the pressure. We are trying to optimize the velocities. So how should our turbine blade be shaped so that we get the best possible flow with minimum losses? So all this we are doing with keeping certain targets and goals. It can be efficiency, it can be performance, it can be optimization, right? So this is what CFD or computational fluid dynamics is all about, right? So now we'll try to look at these NS equations, Navier-Stokes equations, right? These are the governing equations for our flow simulations. Okay. So here, can anyone tell me what form of the NS equations that I am showing you on this slide? What form? Conservative. Okay. Anyone else? Partial. That's good. You're close. Partial PDE. Reynolds transport theorem, RTT, not there yet. So you can see these bold letters, right? F, Q. What are all this? U, they're all in bold, right? F, Q, what are all this? Vector. Excellent. Yes, it's a variable, very good, but it's actually vectorial representation of the Navier-Stokes equations. Very good. So the first equation is the, can anyone tell me what is the first equation? Yes, in 3D, of course. Okay. So it is the vectorial form. Very good. It is continuity or mass conservation equation, right? The second one is, what is the second equation? Momentum. Very good. It's a differential equation. Very good. Partial. And the third one, energy, where ET is the total energy. Okay. So you can see this is a vectorial form, and you can see that it's a, as some of you have pointed out, it's a differential form, right? And they are like vector differential equations, you can also call them. And because of using the vectorial form, the equations looks very compressed, right? Just three equations. So there is the mass continuity, this is the momentum, this is the energy. So we'll try to go to the next slide. Now here, here also we are talking about vectorial only. You can see V cap, V cap, V cap. Here we have given some significance for these terms. If you look at the previous expression and this continuity equation, you can see that dou rho by dt plus del dot rho was equal to 0, right? Now this continuity equation is applicable for which type of flows? So this is the generalized continuity equation which I'm showing here. Dou rho by dou t plus del dot rho v cap or rho u is the generalized equation, but one which I'm showing here is just del dot v equal to 0. So what type of, very good Aditya. So this is the incompressible form, so that rho is rho is constant, at least at that uh, at that point of space or time, so that dou rho by dou t is 0 and del dot rho v becomes del dot v equal to 0 because rho is constant. Okay. So this is the incompressible continuity equation. Great. Now, this is also, now this is the momentum equation. Okay. If you see this, right? So dou rho u by dou t plus u dot del rho u is equal to the shear stresses and the body forces. Okay. So here, what is this derivative called as? Can anyone tell me? Capital dV by dt. Substantial derivative. Excellent. So that is the substantial derivative or the material derivative. Okay. So this comprises of, we can, so this is nothing but so what you're doing here is, so when you're doing dv by dt is nothing but the acceleration, right? So here there is a flow here, right? So the point is not just moving at constant velocity, but also it is moving, right? So here v t, and here it is v t plus delta t. If you look at our coordinate axis, So at t equal to, at certain point t, the velocity was here, v of t, and at some other t plus delta t, the velocity vector has changed the direction also. Okay. So this substantial derivative captures not only the change of velocity magnitude with respect to time, but also because it's a vector, the direction also is changing. The directional part also is captured in this dv by dt in this term. This term is capturing the directional part of the velocity change. Okay. Okay. So yeah. So this is the x-axis. So that is the total derivative, substantial derivative. And you can see that it's nothing but change of velocity with time, and also the convective term, because the velocity is, it is getting transported. You can see that the particle is moving in this in the flow, and its velocity is continuously changing in time. The velocity is a vector, and the direction also is changing. So that is why we have this extra convective term. Okay. So generally, when you say dv by dt is nothing but vt plus t, t plus delta t, that's same definition, right? Limit delta t tends to 0 is a definition. So these are all mathematics, right? This is a vector. And I hope you all remember your vector calculus. I mean, of course, that is what we are trying to do here. So here we are subtracting two vectors, not scalars. So for example, vt t plus delta t was like this, and vt was like this. So when you subtract, right, some this is the what do you call the vectorial difference, right? You're trying to subtract. So this will be your vt plus delta t minus vt. Okay, because vt is this way, vt plus delta t is that way, and when you subtract vt plus delta t minus vt, so you have to reverse the direction. That's like vector addition, and then that will be your dv. You can say effectively this is nothing but your delta v cap. This part. Okay, so you can see definitely the components are all in, it's all over the place, right? So that is what your dv by dt. So we have this, not only there is a change of velocity in time as the liquid flows through the domain, but also there is this convective term that is coming because of the spatial change of velocity or change of velocity in space, right? So now again, this is a vectorial form as I told you. So this is the delta p is nothing but your pressure gradient. So this is nothing but, if you look at the second, you can see this, sorry. So if you look at this equation here, so this rho is nothing but your something like a mass term, and dv by dt is like an acceleration time, right? Acceleration term, right? So the right hand side is nothing but your first term, forces. So if you remember your sigma f is equal to ma, right? This is your typical, what do you call, Newton's law, Newton's second law, right? So here he has just reversed it. Ma is equal to sigma f. Sigma f is nothing but sum of all forces acting on the fluid body. So there are surface forces and there are body forces. So these surface forces are nothing but your pressure. It's a compressive force. And then we have the viscous forces. So both of these two forces are nothing but your surface forces. And this is the body force that is acting on the whole volume of fluid. That is acting on whole volume of fluid, right? But surface forces are acting only in certain parts of the flow, and they are different. And they are different at different points of the flow also. The shear stresses are different, right? The viscous stresses are different. For example, here we are modeling, we are assuming that it's a Newtonian flow, and we are assuming that uh, the 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 shear stress is proportional to velocity gradient, right? So the velocity gradients may change in the flow, and the viscous forces acting on the fluid elements also may vary in the flow, right? So this is the force component on the right side, and the left side is nothing but your mass into acceleration term. Okay. So this del square V is also called as a diffusion term. Okay. So viscosity acts like a diffusion of momentum here, right? So similarly, if you have heat conduction equation, right? If you remember, their thermal conductivity, depending on the thermal conductivity, that is a property. Depending on the thermal conductivity of the material, the heat diffuses either faster or slower in the material. Similarly, here diffusion, the parameter is viscosity. It was thermal conductivity there, it is viscosity here. So depending on the viscosity, the momentum diffuses faster or slower, right? So this is the diffusion term, and this is what we are talking about, the momentum equations. Okay. So till now we have touched upon the vectorial form of our Navier-Stokes equations. We have got some idea of the different terms that are being, the significance, the physical significance. We got some idea, right? It is nothing but this Navier-Stokes equations, or the momentum equation especially, is nothing but Newton's second law applied to the fluid element. Okay. Great. So we'll next move. So now you tell me, again, these are Navier-Stokes equations. Suddenly they look so complicated. Suddenly they look so big, expanded, very complicated. So what are these what is this form of equations? Am I audible now? Am I audible, guys? Am I clear? Okay, thank you. Okay, so Mohammed Sonu is saying it is non-linear PDE. PDE. So very good. This is the differential form, okay, or the partial derivative form of the Navier-Stokes equations, right? So we have seen vector differential, then this is completely, partial derivative equations, partial differential equations, right? So the vectorial forms are all expanded now. Got it? So this is nothing but, okay, this is nothing but your del dot rho u, where u cap, okay, we'll put v instead of confusion. V is the velocity. Doesn't matter. V also is there. So ui, I am just using Cartesian coordinate system for the sake of simplicity. Bj plus wk cap. So ijk, I think you're all aware of. U is the x component of velocity, v is the y component, and w is the w component of the velocity, right? V vector. So del dot rho v, if you expand, this is how it looks like. So is density a scalar or a vector? Okay, Charan Sai. Very good. Anmol, Arun. Great. Everyone. So we'll just quickly go through it a little bit later. What scalar and vector? I think most of you know. So this is what we did. So we opened up this vectorial form, and when we open it up, you suddenly see these guys are all becoming bigger. Even this one, this whole term, and you can see suddenly we got three components: x component, y component, z component. If you remember, All these three were nicely packed up into one box. That's all. Now, when you start writing component wise, they suddenly open up into three components. Why? Because when you're talking about momentum, momentum is a vector. Continuity, we are dealing with mass, it's a scalar. So one equation for continuity. Similarly, energy is again a scalar quantity, just one equation. Right? So suddenly all these terms opened up, and you suddenly see they are like looking crazy, right? But in fact, they were nicely packed up. If you looked up here, if you look it here, in this B dot del B, this whole term was nothing but B dot del B. And when you open up component wise, all this will come. And these are all nothing but the viscous stresses, tau xs, tau xy, tau xz, and all. Okay. And they are actually written in terms of for a Newtonian fluid, right? This are all functions of viscosity and velocity gradients, and they will become simplified. So this is general form of equation, and this is the energy equation. Again, you see, this is nothing but your pressure gradient term. This is your heat conduction term. So this is a diffusion term. This is the work done by viscous forces. So energy, this is nothing but the work, right? If you remember energy equation, it is nothing but if you look at your, this is derived from your first law, right? Delta E is equal to delta Q minus delta W, right? This is the work done, this is the heat added, this is the energy change. So this is what is coming out from your, this is the starting point for your energy equation. So work is done by not only the pressure forces. If you remember pressure, PDV is the work, right? So when work is done on the system, we say it's negative. When work is done by the system, we say it is positive, right? So this is work, and this will also go. So that is why this is nothing but your work done by the shear stresses. This is work done by your pressure forces, and this is nothing but the heat delta Q term getting modified. Okay, heat diffusion. And there might be some more things, like, for example, if you have some reacting flow, so some heat is liberated, some Q dot heat is generated by reactions. For example, if you are burning something, a rocket, combustion chamber, so we'll have extra terms in the energy equation. Okay, and because of these extra terms, energy ultimately will be, at least in the gaseous cases, will be shown as temperature, right? So this is the full 3D unsteady Navier-Stokes equations. Okay. Now tell me what form of these equations are for Navier-Stokes. Do you think these are again Navier-Stokes or not? Are these Navier-Stokes equations or not? Anmol is saying no. Tanna is saying RTT. Yes, Reynolds number and Prandtl number, correct. Yes, these are integral form of equations that are derived from your, very good, Rafiq, Kamal Jyoti, very good, very good. These are all integral form of equations. So you can see there are so many forms, and these are generally, as some of you have told, it is coming from the Reynolds transport theorem. That's great. And these are the equations. These type of equations are actually being used in the finite volume methods. Control volume for fluids, at least the finite volume method is very popular and convenient also. So they use this integral form of approach for your CFD, solving the Navier-Stokes equations in CFD. So the first one is the continuity equation again. The second one, as most of you guessed, it will be the momentum equation. I didn't put the energy equation because it will be another 2 lines long. Not necessarily confuse us. So here also this omega is nothing but your volume integral. S is nothing but the surface integral. Okay. Omega is volume integral and S is your surface. So if you have a 3D, for example, box or something. So this is your volume and these are your surfaces. Surfaces, outer faces are all called the surfaces. The outer surfaces of the box are the surfaces, that is the surface integral. And the volume contained in the box is nothing but your volume, omega. So every volume has some surface enclosing, right? So that is what we are showing here. The first one is the um, conservation of mass or continuity equation. The second one is the momentum equation. Here tau is your shear stresses, as you can see, and this minus P is nothing but your pressure forces. So pressure and shear, and you can see both are acting on the surfaces. Pressure and shear stress are acting on the surfaces. If there is a body force term, it will act on the volume. Okay, it will act on the volume. So clear, guys. So far, so good. Everyone is able to follow. Just put so far so good SFSG or something in the chat box, so I'll know something. Or IGI, I got it. Yeah, great. Thank you. Thank you very much. Great. Okay, so now we'll go to the basic math for CFD. As I told you, we would like to create some series of boot camps here. This is like the first of its kind in our at Skill-Lync. So math for describing. So why is mathematics coming here? Because we have to understand the physics. It can be, as I told you, fluid dynamics, heat transfer. You have so many equations, right, that you have done in undergrad. We have conduction, Fourier law of conduction. We have Laplace equation. We have Poisson equation. We have Burger's equation. Navier-Stokes. I mean, there are so many equations. There are like so all of these phenomena are represented by mathematics. The physical phenomena are represented by mathematical equations, right? So for that, mostly it is calculus. So that's why we have in our BTech so many courses on calculus, vector calculus, ODE and PD. Why do you think all these four are being studied in your BTech? We say math 1, math 2, math 3, and math 4, right? Essentially, we are trying to study the mathematics necessary to understand and also create your own equations for understanding the physical phenomena that we are observing outside in nature, for example. So another thing, so this is the basic mathematics on the equations on the classical fundamental aspect. But then also we need additional mathematics for numerically solving the governing equations. Generally in CFD, the governing equation is nothing but partial differential equations. So if you take any simulation, for example, even if you take structural simulations, or if we take some electronics simulations, magneto-hydrodynamic simulations, electrodynamic simulations, take any field, every field the same thing will apply. You can go to any branch. This is typically the mathematics that is required, especially when you are in the simulation side of things. So you need to understand calculus, vector analysis, ODEs, and partial differential equations. And then to solve these PDEs and ODEs, we need to know linear algebra. right? And remember, most of the linear algebra also is being taught in our colleges and universities, right? Amazing, right? So that is how the mathematics that we are using, what we are learning in our undergrad is being applied in CFD, for example, right? So we might have studied it. We were just solving things. We were just going through these things, but now we'll try to understand how those things that you learned in your undergrad are actually being applied, right? To solve this PDE equations and to get some insights about all this from the CFD simulations, right? So actually today I'll mostly look at some basic vector analysis part only. Maybe later we will maybe part 2 or something, we'll try to enter into PDEs and all that. So here today we'll mostly cover, as I told you, we just looked at Navier-Stokes equation, some little vector analysis, and then maybe in the end we'll talk about Reynolds transport theorem, and then we'll close it. Okay. So this is the coordinate system. I think you're already aware of your Cartesian coordinate system we are talking about. So can anyone tell me which type of coordinate system is this? In the chat box, just by looking at it. What type of coordinate system is this? I hope everyone is aware of the Cartesian coordinate system, right? I skipped it because maybe it's too basic, but next time maybe I'll cover it. So it is nothing but our X, Y, and Z, the right angle system that we regularly use is the Cartesian coordinate system. Great. Most of you have answered it right. It is not exactly polar coordinates. It is a cylindrical coordinate system. Okay, polar coordinates are generally like 2D. Cylindrical coordinate is nothing but adding third element, r, theta, and z. So this is cylindrical coordinate system. So if you look at the first figure, any point, for example, this is the point here. So this is the point P, right? So that point P is expressed by r, theta, and z. So r is the, you can see, so r theta is the polar coordinates, the z will make it cylindrical coordinates. So as most of you answered it correctly. So this, the same, and so you can see theta, unit vector of theta, something is, just a second, there's some. So here, theta cap, r cap, and z cap. What are these three things called as? Theta cap, r cap, z cap. Not axis, z cap, theta cap, and r cap. Cylinder coordinates. Okay, can you tell me? So, unit vectors. Very good. Sonu and other people who have answered, unit vector is correct. Anmol. So these are nothing but the unit vector directions. If you remember in Cartesian coordinate system, we have I, J, and K, right? Similarly, here we have unit vectors in the radial direction. R is nothing but the radial direction. Theta is nothing but the tangential direction, right? R and theta are mutually perpendicular. And Z you can see is your axial direction. And you can see these three vectors are again mutually perpendicular to each other. They form like a basis vectors, unit vectors, whatever you want to call. So this P cap has coordinates given by R, theta, and C. The same P, if you bring it to Cartesian coordinate system, that P coordinate system will be, so R is this vector R is the radius, and then you take it vertically, it will go to point P, right? So r cos theta is your x component. R sin theta is your y component. So this x, this y, the z remains the same. Okay, the z coordinate remains the same. Everyone clear on this? So r is nothing but root x square plus y square. So if you draw a line, right? Sorry. And something like this. So this is theta. So r cos theta will be x. This will be your y. This is perpendicular actually. Okay, this is perpendicular. So r cos theta is some o m. If you put OM is your x coordinate, MQ is parallel to the y. So MQ is your y coordinate, and Z is your Z coordinate anyway for point P. So XYZ, X is equal to r cos theta, Y is equal to r sin theta, and you know. So theta is nothing but tan inverse y by x, right? Very clear. And Z is equal to Z. And r can obviously, you can see, extend from 0 to infinity. So this is your r. R vector can it has unlimited bounds, but it's positive, obviously 0 to infinity. Theta can vary from 0 to 2 pi. So theta can make a complete circle. This is your theta, right? It can make a complete circle, right? Theta can vary complete circle. As Z obviously can go from minus infinity to plus infinity. Minus because it can go even negative direction, right? So the volume element also, I think you're all aware of. So r dr d theta dz. So if you take a cylindrical element, volume element, so if you try to do the math, so you'll get, so r d theta dr into dz. That's how you write it out. So this is your infinitesimal volume element. Similarly, the line element is given by this expression. Okay. That is the uh, that is the it can also be called the distance vector along the curve. So if you have the cylindrical coordinate system, if you have a curve like this, so the s coordinate is along the curve. Okay. And ds is nothing but is given by this expression. Okay. So similarly, next we'll go to, I think most of you can guess it. This is a spherical coordinate system. This is a little bit harder, but not very difficult. Okay. So here you can imagine something like the globe. Like we have the earth, right? Earth is a sphere. The center of the earth is like the origin. And we are all on the surface of the earth, right? India is here, Australia is there, China, Europe, America, all of them are scattered along the globe. The thing is, but generally because it's a isosurface, because earth is like a, mostly the radius doesn't change a lot, but still of course changes. It's a little flatter at the poles, right? So radius is not uniform for our earth, but you can. So here you can see that any position, for example, Chennai, Bombay, they have something called as, can anyone tell me latitude and longitude? So Bombay will have a particular latitude and longitude. Only Bombay will have that latitude and longitude. There might be many cities on the same longitude. There may be many cities on the same latitude, but Bombay will have a unique latitude and longitude. So any point on the sphere will have a unique latitude and longitude. Here, if you look at this sphere example here, can anyone tell me what the latitude angle and longitude angle corresponds to when this theta and phi? So we have theta angle and phi angle. So which is corresponding to latitude and which is corresponding to longitude? Can I see that in the chat box? So you have a city on latitude angle, theta and phi. Use the words theta and phi. If you remember, I remember latitude longitude for Hyderabad. So Hyderabad latitude is 17 degrees. Okay. Longitude is around 80 degrees east. Okay. That this are both of them are angles. Very good. People are trying. Utkarsh, Shah, Aditya, very nice. So latitude is your phi. Great. So latitude is your phi. This is but the elevation from the equator, right? If you cut it, the spherical coordinate system from the equator, the latitude keeps increasing. At poles, the latitude is 90 degrees. This is the pole, right? This is the North Pole. This is South Pole. So latitude is 90 degrees. And at equator, latitude is 0 degrees, obviously. Similarly, this theta is the also called as azimuthal angle, right? Or so just remember it's like a longitude. And when you try to bring it to the Cartesian coordinate system, again, the same point P, that same point P here again, you can see r cap, theta cap, and phi cap are unit vectors in the spherical coordinate system. And when you try to bring it to the Cartesian coordinate system, what happens? So this is your point P. What are its x, y, and z, right? When in terms of r theta and phi. So if this is r, this is the radius vector or radius for the sphere. So z is nothing but r cos theta, right? This is hypotenuse, this is right angle. R cos theta is nothing but the z in the Cartesian coordinate system. And when you bring it down, so this so this is the r sin theta part. This is r cos theta. This is the r sin theta. The same r sin theta falls here on the floor of xy plane. So r sin theta cos phi. This is the cos phi. Now phi comes. Phi is your azimuthal angle, right? It can rotate from 0 to pi. Okay. So r sin theta cos phi, the same thing like our polar coordinates. I mean our cylinder coordinate system, right? So r sin theta cos phi is your x. R sin theta sin phi is your y. So this is your r sin theta sin phi, and this is your r sin theta cos phi. So you can see how we can convert interchangeably between spherical coordinate system and a Cartesian coordinate system, right? So this is the way of converting from spherical to Cartesian. R is nothing but root x square plus y square plus z square, right? That is nothing but your x, y, z values, right? Nothing but the distance between point P and the origin. So if you have a in the Cartesian coordinate system, if you have a point P, right, with x, y, and z, the distance. So this is your origin, right? So distance of the point P from your origin will be root of x square plus y square plus z square. I think all of you know this. So anyway, we'll go a little bit deeper into it in the upcoming webinars. Very interesting stuff we can discuss on vector analysis itself. So R is going from 0 to infinity, right? Again, if you remember cylinder coordinates also, the radius vector is always going from 0 to infinity. There is no negative number there because it's a radius or it's a distance vector. So that can never be negative. And theta, as you can see, so if you look at this theta, don't get confused. This is another picture. We'll try to look at this picture. So theta is azimuthal direction. It can go complete 0 to 2 pi. And phi, goes from 0 to pi. Okay, so here 0, it goes from 0 to pi. So pi is here 180 degrees. Okay, 0 to pi. So this is your theta angle. It can go from 0 to pi. So here also we have area element and the volume element also. So you might have used this in the double integral, triple integrals. If you remember in your BTech, right? Double integral, triple integral when you're doing with using spherical coordinates, cylindrical coordinates. We have used this different volume elements. We'll go into it maybe in the subsequent bootcamp webinars. But this is just a intro to like what things are and what are the important things that we need to know to understand these equations and the way to solve them also, right? Now, so from vector calculus, that was just an intro little bit. Now we'll try to come out because we don't have much time. It's already 8:10. So let me, maybe in 5-10 minutes, we'll cover some gradient and all that. Maybe RTT will cover later because 8:30, I should not. Okay, I'll just share you one more. So far so good, guys. Everyone is able to follow, I hope. So I'll just show you some quick stuff here, right? So I think vector and scalar, we know. This is the Nabla operator, Nabla or the del operator, right? So this is the del operator we have seen in the Navier-Stokes equations. And the del operator or the Nabla operator is given by this expression. Basically, this operator, it's an operator. It operates on vectors and scalars, right? So it takes the partial derivatives in all the directions for a given variable. All the directions means in the three principal directions. It can be I, J, K, R theta phi, or R theta Z. So in all the directions, and so partial derivation. I think you all know the derivative concept, right? So if you have a function, some f of x, right? I'm just explaining in the 1D sense. I'm not even talking about 2D here. So f of x plus delta x, right? So df by dx is nothing but f of x plus delta x. So this is the typical calculus that we always use. Limit delta x tend to 0. So generally f dash x is called also remained as a f dash x, right? So generally this is also called a slope, by the way, right? So that's why when you have this, when you're taking this partial derivatives, it's all about if you apply it for delta phi, for example, right? Where phi is a scalar, we get I dou phi by dou x. So dou phi by dou x is the partial derivative of function phi in the direction of I. Okay. Similarly, j dou phi by dou y, it's a cumulative. So for example, you are standing on a hill, right? You're standing on a hill. The slope going upwards may be different from the slope going sidewards, right? Or some other angle also. So this is what gradient is trying to tell you. If you're trying to climb in the I direction, you have a slope of dou phi by dou x. If you try to go in the y direction, your slope is going to be this. If you're going to go in the z direction, maybe some other direction, your slope is going to be this. So this delta phi is trying to give you the directional derivatives or gradient. So simplest thing is you climbing a hill. Sometimes you will see going downward will be very steep. Sometimes this will be more convenient. You know, the slopes are different in different directions, especially for your when you're climbing a hill or when you're taking different paths, right? So here also this del operator will give you an idea about how the function is varying from that point when you're trying to move into some other direction. So if I'm going from P to Q, how does my gradient change? If I go to P to Q prime, how does my gradient change? So that Nabla operator will help you. That is the gradient. Nabla operator is used to get those gradients, right? Yeah. So the gradient of U is defined by this expression. So gradient of U is if U is a scalar field, right? If U is a scalar field, what can be a scalar field in fluid dynamics? It can be temperature, it can be pressure, it can be concentration of species. All these are scalar field. So temperature can vary. If, for example, if I take a 2D domain, T is a function of xy, right? So similarly, pressure is a form of xy. So pressure is here different. It's different here. It's different here. In this whole plane, the pressure and temperature are scalars, and that is scalar field. So if we have such a scalar field, then the gradient of the scalar field is given by this vector. So this gradient operator actually converts the scalar field into a vector field. Okay. So for example, here we have this scalar field given by u of xy as minus x square and minus y square. And if you do the gradient of u as using this simple relationship, so dou u by dou x, right? When you do that, so this minus x square minus y square should be there. Some typo is happening. So when you do that, you get this minus 2xi minus 2yj plus 0k. What does 0k mean? That there is no gradient in the z direction. Okay, there is no gradient in the z direction. That is, the function doesn't change in the z direction, right? So this is the gradient operator. And if you try to plot the gradient, so x and y and z is nothing but your del u, right? This is your del u. This is how your, and you see everything is negative, right? If you remember del u is nothing but minus 2xi minus 2yj plus 0k. So when you do the gradient u operator, you can see your gradient is highest, or it just, so the gradient actually gives you, tends to point in the direction of greatest change of function. So here you can see how all the vector fields are pointing to the center. That is where the highest, you can say, this gradient is happening. So I think I will stop here in the interest of time. It's already 8:15. I wanted to cover the divergence, more of gradient and Reynolds transport theorem also. Uh, Apologize, I couldn't cover all that. But I hope it was useful to you. We'll have some more webinars more deeper into these topics, and we all will learn together.